I think ABBA is probably one of the greatest bands ever. And if you disagree with that, you're going to have to fight me. Anyways, let's talk about the conservation of momentum. Previously, what we've been doing in this class is we've been talking about impulse and momentum. You know, Ft, or an impulse, equals some mass times a change in velocity. But what's actually happening there is once we have an object in motion, something with mass in motion has momentum, it's going to conserve that momentum. And when we're talking about conservation of momentum of an isolated system, so this means that nothing on the outside is acting on it. So we're not going to be talking about like hockey sticks, interacting with a puck, or a force like a wind blowing and pushing something. When we talk about an isolated system, two objects that might be moving or might not be moving, and that's it. That is the entire little world there. That is an isolated system. And when we talk about momentum of an isolated system, that total momentum is constant. It is not changing. It must be conserved. This is another conservation law, like some of them you might have learned in the past. Conservation of mass, conservation of energy. Really, they're the same thing. Thanks, Einstein, E equals mc squared. But this is another conservation law. Momentum must be conserved. All the total momentum in an isolated system is constant. So, if we wanted to write this on a mathematical level, what we could say is that for an isolated system, the change of momentum is equal to 0. There is no change in momentum for an isolated system. When we have a set of objects or parts of a single object, that's a system. And if they're isolated, there's no external forces. There's no impulses that could act on these. So the change in momentum has to be 0. We can pass momentum from one thing to the other, but the total net momentum is not changing. Okay? We're going to talk about this in this class for two objects in a system. Like if you had a bowling ball and a bowling pin. That's two objects. The bowling ball, the bowling pin. You can expand this to a 300, 400, 500 body system. And the same rules apply. It just becomes a longer problem, and normally we just force the computers to do it, but the same principles will remain as we go through all this. We're going to do this with 2, because if you can do it with 2, you can do it with 3, you can do it with 4, it just takes more time. So if we did this for a 2-object system, we can actually expand this delta P equals 0 into the following. And you don't have to write this immediately, but as a little sidebar, remember, a delta P represents a final minus an initial momentum. That is what delta P represents. So what we can actually say here is if we move the initial momentum to the other side, we can say that the final equals the initial, or if we flip-flop them, we could say that the initial equals the final. So for a 2-object system, or a 2-body system as we sometimes call them, we can write this. The momentum of the first object initially plus the momentum of the second object initially. This would be like if you had cars moving, right? My car and your car. This must equal the momentum of the first object on a final position at the end plus the momentum of the second object at some final state. So maybe I'm driving and you're driving, and then we crash. If we're the only objects there, we are an isolated system, there's no outside forces, it's just us. We have some initial momentum, and we have final momentums. If we wanted to expand this, a nice way to expand this is to take all the momentums and to write them as mv. So this is going to look a little long, and you might kind of like spread onto some other part of the page. But if we wanted to spread this out, we could write all those momentums as m1 v1i. So that's the initial momentum there, plus m2 v2i. That's the initial momentum of the second object. And this would have to equal m1 v1f, that's the final momentum of the first object, and you see where we're going with this, plus m2 v2f, final momentum of the second object. This right here, we're going to be using that a lot. That is going to be the bulk of what we are doing. And that equation looks giant. It looks like it's got 4 pieces to it. Each piece is 2 parts, so there's 8 parts in that equation. Oh no, they're velocities, and they've got directions, because they're vectors. But as we're going to see, whenever we draw a picture here, this equation is actually very straightforward for us. And sometimes we get perfect problem setups so that a lot of the things in this equation end up going away, which is a very nice thing for us to do when we're starting to look at conservation of momentum. Now, the first type of momentum conservation we're going to look at is the idea of a separating system. So imagine you have a bowling ball and then it explodes. Don't ask me how a bowling ball just exploded, but it did. Well, this means that you have many pieces of the bowling ball going in different directions. And if that bowling ball was just sitting there initially, the bowling ball's initial momentum was 0. It wasn't moving. Which means that the final momentum has to also be 0. Well, how could it be 0 if everything on the bowling ball is moving now? It's exploding. It's going everywhere. Well, remember, velocity is a vector and momentum is a vector. So if you have a piece of the bowling ball going this way and a piece of the bowling ball going this way, their momentums can be equal and opposite, such that if we added these momentum vectors together, they would have to add up to whatever momentum we had in the beginning. And if that bowling ball is at rest, they'd add up to 0. Okay? So that's what we're going to start looking at here for our first conservation momentum, separating systems. Objects that are initially at rest, and then they move apart for some reason. Maybe an explosion, maybe just internal forces, whatever. Okay? But the key thing to remember here is we've got 2 directions. Directions matter. You know, which direction's positive, which direction is negative. We need to make those decisions and then work those through. So let's take a look at this first example problem for a separation scenario. Now, one of the greatest movies of all time in terms of figure skating is Blades of Glory. And if you've never done an Iron Lotus, don't attempt one. And if you don't know what I'm talking about, well, you need to catch up. But we've got 2 ice skaters on an ice rink. And we like to pick an ice rink here because it's a frictionless surface. So let's just make our little ice rink here. Let's draw a picture like Grandpappy Bots taught us to do. And here's our poorly drawn ice skaters. One's got a red cape, and the other one has a blue cape. They start at rest. You know, just like at the beginning of their piece, you know, the song isn't on yet. They're just at rest. They're getting ready to go. And their first epic move is to push off from one another and move away from each other on the rink to begin their routine. So we know they are initially at rest, which means the initial velocity of skater 1 and the initial velocity of skater 2 are both 0 meters per second. Because they're not moving. They are at rest. When they push off against one another, the 45 kilogram skater gains a velocity of 0.62 meters per second. So that's the first skater's final velocity. And we know this skater's mass here is 45 kilograms. Our second skater, when they push off, they are gaining a velocity of 0.89 meters per second. We are trying to figure out what is that other skater's mass. What is the mass of that other skater there? Well, we've drawn ourselves a nice picture. We've put arrows in it, which is very, very helpful. and we know the conservation of momentum equation. Momentum's initial added together equals momentum finals. So let's go ahead and use that equation and just be careful about our directions. So if we think about what our initial momentums are, well, the initial momentum of the first object and the initial momentum of the second object here, both of them have an initial velocity of 0. So the initial momentum of 0 plus 0 is 0. Like, that's great for us. Because before, we were looking up here at this equation, we're like, oh my goodness, like we've got a bunch of things at the beginning. Look at all this right here we have to deal with. Well, in this problem, in this separation, because we were not moving, that just went away. It just became 0. A very nice thing that occurred for us. This has to equal to the MVs of the other parts. So, or the momentums of the final. So our final momentum, that's a mass, 45 kilograms, multiplied by a velocity. So I'm going to leave a space here. You're going to see why in a second. There's the 0.62. And we need to add this to the mass of the second skater. We don't know their mass, so there's M2 multiplied by a velocity, 0.89. And if we actually try to solve it just as it's set up right now, we would have to try to subtract the red numbers onto the left side and then divide by 0.89. But that would give us a negative mass. And you can't have a negative mass. We would immediately see that something is wrong in this problem. And that means that we're missing some negatives here. Well, when we look at our two figure skaters, one of them is moving to the right, one of them is moving to the left. Because they have velocities, we need to make a decision. What direction are we calling positive? What direction are we calling negative? This is not a new decision for us. We've made these decisions hundreds of times now. It doesn't matter what you actually pick, but a decision needs to be made. So what would we like positive and negative to be? Sure. Classically in physics, we could say right is positive. That's kind of like the math thing, right? On the x-axis. So if left is negative here, this 0.62 is actually a negative 0.62. This 0.89 stays positive. And this allows us to just go ahead and start solving this. If we pull out our trusty calculadoras, we can take 45 times negative 0.62, and we get negative 27.9, and that's going to be plus M2 times 0.89, and all this equals 0. Let's add the 27.9 to the other side. So we get, whoa, that's just janky looking, isn't it? 27.9 equals M2 times 0.89. And then if we just divide by 0.89 on each side, we find the value of M2, the mass of the second skater, and we quickly see here that their mass is, let's see, 27.9 divided by 0.89 is 31.35 kilograms. If we kind of think about that answer, we got an answer of 31.35 kilograms. Does that answer even make sense? Well, the skater on the right, skater 2, they moved faster than the skater on the left. Now, if these skaters push off from one another, they have the same force pushing off. That's a Newton's third law there. So in theory, the less massive skater should gain more velocity, which they do. The less massive skater ended up with 0.89. The more massive skater ended up with 0.62. So that makes sense from a force perspective if we kind of think about it that way and what we know in our real lives, and it makes sense from a conservation of momentum. So that's our first type of problems for the conservation of momentum here, these separation problems. Oftentimes these problems are going to have initial momentums of 0 because the objects will not be moving, and then they will explode or release or separate in somehow, and then we'll have to put together those conservation momentums on the second part there. And just remember, we've got positives, we've got negatives, and that's physics. So this problem is finished. Check out our next two examples on this for some extra practice. And until next time, adios, and take it easy.